Bismillahirrahmanirrahim. Uh, Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. So, in this lecture, I will demonstrate you another method of solving higher order ordinary differential equations. And in this method, we will transform nth order differential equation to n first order differential equations. Right, so every nth order linear differential equation is equivalent to a system of n first order linear equations. For example, we are given a general ODE as a n y nth derivative of y plus a n minus 1 into n minus 1th derivative of y plus so on, plus a2 second derivative of y plus a1 first derivative of y plus a naught y equal to dt. So in this general equation, we have to make some substitutions, and let's assume that x1 is equal to y. Okay, so x2 is x1 derivative, right? So x1 is equal to y, x2 is equal to derivative of y, x3 is equal to double derivative of y, and so on. Xn is equal to n minus 1th derivative of y, and xnth derivative, the derivative of xn is equal to nth derivative of y. So we will make such a substitutions, and after making such a substitutions, we will see that derivative of x1 is equal to y derivative, and y derivative is equal to x2. So x1 derivative is equal to x2. Similarly, x2 derivative is equal to x3, x3 derivative is equal to x4, and x minus 1 derivative is equal to xn, and finally we will have xn derivative, and xn derivative is equal to nth derivative of y, and that will be evaluated by rearranging this general ODE, right? So xn derivative can be written as yn, and yn is basically equal to minus a naught y minus a1 y derivative minus a2 y double derivative and so on, minus a n minus 2 y n minus 2 minus a n minus 1 y n minus 1, and divided by 1 over a n. All terms will be divided by 1 over a n, and plus gt. So gt will also be there at the right hand side, and at it will be divided by a n as well. So this is our xn derivative, and it is equal to minus a naught x1 divided by a n minus a1 over a n x2 minus a2 over a n x3 and so on, minus a n minus 1 divided by a n xn, and this is our gt, right? So this actually y is represented by x1, y derivative is written as x2, y double derivative is written as x3. So that's why we see x1, x2, and x3 over here. So this set of equations can be written in the matrix form. Okay, so that will give us the form of x derivative equal to ax. So this will be a matrix, and here we will have a column vector, and that will contain x1, x2, x3 in the column, and here we will have x1 derivative, x2 derivative up to xn derivative, and that will be called as x derivative column vector. So it will be equal to a matrix times x column vector. So let's solve some examples, and then this concept will be clearer. So convert each linear equation into a system of first order equations, and we are given this second order ODE. So again make the same substitution. So x1 is equal to y, and x2 is equal to y derivative, x2 derivative is equal to y double derivative, and y double derivative is equal to 4x2 minus 5x1. So it will be shifted to the right hand side, and it will become 4y derivative minus 5y, and y derivative is equal to x2, and y is equal to x1. So it will become 4x2 minus 5x1. So x1 derivative is equal to x2, right? X1 derivative is equal to y derivative, and y derivative is equal to x2. So first equation is x1 derivative is equal to x2, and second equation is x2 derivative is equal to minus 5x1 plus 4x2. So in the matrix form, it will be written as follows: x1 derivative is equal to x1, x1 derivative equal to x2, and x2 derivative is equal to minus 5x1 plus 4x2. So this is x derivative equal to ax. This is our A matrix. So this is how we can transform nth order differential equation into n first order differential equations. And after evaluating this form, we have to evaluate eigenvalues and eigenvectors of this A matrix. Okay. So after evaluating the A matrix, its eigenvalues are computed by assuming lambda I minus A determinant equal to 0 and solving for lambda. So this is the traditional or standard method of evaluating eigenvalues. So we are given A matrix. So multiply lambda by an identity matrix of the same order and subtract A matrix from this and take the determinant of the resultant matrix and equate that determinant to 0. So this equation will be obtained. This is lambda I and this is A. So for example, A has entries of A, B, C, D. Then after subtracting this matrix from this, we will have this matrix lambda minus A, 0 minus B. So this is minus B, this is minus C, and this is lambda minus D. Take its determinant, and its determinant is equal to lambda minus A into lambda minus D minus BC equal to 0. And this is called characteristic equation, and we have to evaluate the roots of this differential equation, that those roots will be lambda 1 and lambda 2, and those will be the eigenvalues. So the solution will give two values of lambda, that is lambda 1 and lambda 2, and those will be the eigenvalues of this A matrix. Okay, so next step is to evaluate the corresponding eigenvectors k1 and k2, and these eigenvectors are evaluated by assuming ax equal to lambda x, right? So A is the original matrix, and x is the column vector equal to lambda x. So K1 will be evaluated first, and it will have two entries x1 and x2. So K1 will be evaluated corresponding to lambda 1, K2 will be evaluated corresponding to lambda 2, and they will be two eigenvectors and they will contain two entries each. So general solution is evaluated from one of the following possibilities. If we have two distinct and real eigenvalues of A, then the general solution will be of the form x equal to c1 k1 e raised to power r1 t plus c2 k2 e raised to power r2 t, and we have two eigenvalues and they are distinct and real, r1 and r2. So if we have complex conjugate eigenvalues of A, r plus iota u, r minus iota u, this can also be the possibility of eigenvalues. Then general solution will be equal to c1 k1 e raised to power r1 plus iota u t plus c2 k2 e raised to power r minus iota u. If we have two complex eigenvalues, then they will be complex conjugate of each other, and their real and imaginary parts will be equal. So this is r plus iota u, this is r minus iota u, and this will be the general form of the solution. And if we have repeated real eigenvalues of A, for example, both eigenvalues are equal to same number r, and they are real, then general solution will be of the form x equal to c1 k1 e raised to power rt plus c2 k2 e raised to power rt. So this is how we can solve the higher order ordinary differential equation using eigenvalue method. And let's solve an example to clarify this concept. So we are given this homogeneous ordinary differential equation because its right hand side is equal to 0, and we are given two initial conditions as well. So let's convert into two first order ODEs. So x1 equal to y, x2 equal to y derivative, and x1 derivative will be equal to x2, right? X1 derivative is equal to x2, and x2 derivative is equal to y double derivative. X2 derivative is equal to y double derivative, and that will be equal to 3 by 2y minus 5 by 2 y derivative, and y is equal to x1 and y derivative is equal to x2, so it will become x2 derivative equal to 3 by 2 x1 minus 5 by 2 x2. So let's write them in the matrix form. X1 derivative is equal to x2, so it will be 0 1, and it will be x2 derivative 3 by 2 minus 5 by 2 x1 x2, and this is our system matrix A. X derivative is equal to ax, and this is the vector of initial conditions x1 x2, because we are given initial conditions of y and y derivative, and y is equal to x1, y derivative is equal to x2, so we have x1 0 x2 0 equal to minus 4 and 9. So this is the vector of initial conditions. So let's evaluate the eigenvalues of this A matrix. Okay, so lambda I minus A determinant is equal to determinant of this matrix, and that should be equal to 0. So let's evaluate the characteristic equation first. And after solving this characteristic equation, these are the two roots which are real and distinct. And now lambda 1 and lambda 2 are the two eigenvalues. So corresponding to lambda 1, we will first evaluate the first eigenvector. So ax is equal to lambda 1 x. This is a, this is x, x is x1, x2 is equal to minus 3. Again, this is x, right? Ax is equal to lambda 1 x. So let's write two equations, and it will become x2 equal to minus 3 x1. This is the first equation, and 3 by 2 x1 minus 5 by 2 x2 is equal to minus 3 x2. This is the second equation. Let's put this x2 into the second equation, and we will have 3 by 2 x1 plus 15 by 2 x1. So x2 is equal to minus 3 x1 will be substituted over here, and that is equal to minus 3 x2. So right hand side will be kept as same, and after simplifying this equation, we will have minus 3 x1 equal to x2 at the end. So let's assume that x1 is equal to 1, then x2 will be equal to minus 3. So this is our first eigenvector. So 1 minus 3, we can assume any value of x, but we actually want to avoid the fractions. So we want to get the whole numbers of both the entries of the eigenvector. So that's why we have, and we want to make these entries simple, the simplest. So that's why I have considered x1 equal to 1 and x2 will be equal to minus 3. So this is the first eigenvector. Now let's evaluate the second eigenvector by considering the second eigenvalue of 1 by 2. So ax is equal to lambda 2x. So this is our matrix. Again, make two equations, x2 equal to 1 by 2 x1 and 3 by 2 x1 minus 5 by 2 x2 is equal to 1 by 2 x2, and put this value of x2 over here. So 3 by 2 x1 minus 5 by 4 x1 equal to 1 by 2 x2. So let's simplify this. X2 is equal to 1 by 2 x1, and let's assume that x1 is equal to 2. So x2 will be equal to 1. So again, we want to get whole numbers and we want to avoid the fractions. So x1 is equal to 2, x2 is equal to 1. So 2, 1 is our second eigenvector. Now the general solution will be in this form. Xt is equal to c1 e raised to power minus 3t 1 minus 3 plus e2 e raised to power t by 2. This is 1 by 2 is the second eigenvalue, minus 3 is the first eigenvalue, and the corresponding eigenvector is 1 minus 3, and its corresponding eigenvector is 2, 1. Now we will find out c1 and c2 based on the initial conditions. This is our initial conditions vector. X0 is equal to minus 4, 9, and let's put this initial condition in this equation. So x0 is equal to minus 4, 9. Minus 4, 9 is equal to c1 1 minus 3 because t is 0, so e raised to power 0 will be 1 plus c2 2, 1. So it will also be equal to 0 at t is equal to 0. So this equation will give us actually two equations. Minus 4 is equal to c1 plus 2c2, and 9 is equal to minus 3 c1 plus c2. And we have two equations and we have two unknowns. So c1 and c2 are evaluated as minus 22 by 7 and minus 3 by 7. Let's put these in the original solution. This is the original solution, and this is yt equal to minus 22 by 7 e raised to power minus 3t minus 6 by 7 e raised to power t by 2. And we can also write it in the matrix form or column vector form. Xt will be equal to, here you will put c1 and c2, so we will get this form of the solution. And it actually has x1 and x2, right? So x1 will be the upper solution, upper equation, x2 will be the lower solution. And I have written the upper solution x1t, which is equal to yt, and that is equal to minus 22 by 7 e raised to power minus 3t minus 6 by 7 e raised to power t by 2. Similarly, we can also write the value of x2t. Okay, so that will be equal to 66 by 7 e raised to power minus 3t minus 3 by 7 e raised to power t by 2. That will be x2, or we can say that that will be y derivative. So y derivative is also evaluated and yt is also evaluated, but we need the solution which is yt. So this is our required solution. So I hope you have understood the solution of ODEs using eigenvalue method, and this method is useful for solving higher order ODEs because we can write the equations in the matrix form, and matrix form is, I think, simpler to solve. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.